So myself, Nagarajan, yes, working as product lead for piping design with image graphics software solutions. So what is that we'll be seeing? First, the basic introduction of jacketed piping. What exactly is jacketed piping? What are the components which come into picture of our jacketed piping? Everything we'll be looking out. And also what major stresses we need to perform using our jacketed piping, which is a brief things. Standard checks which most of our piping specifications come out for our jacketed piping requirements. That's what we'll be performing it in Caesar. First, introduction. So what is jacket piping and where exactly it is used? It's a piping segment commonly used to convey various viscous process fluids. So now when I speak about viscous process fluids, suppose say there's a process fluid which at a particular atmospheric conditions or less than atmospheric conditions or something closer to our atmospheric conditions converts into a solid format or a hard format or something. So in that conditions, so to maintain that fluid in the fluid state, we provide an external pipe where steam or hot water or hot oil is used as a heating medium, which is called the jacket. The core pipe is nothing but the actual pipe through which my actual fluid flows, and the outer pipe is called my jacket, where my steam or the hot pipe or the hot water or hot oil everything flows. So in this segment, so this is a small pictorial representation of the same. So what are those things which will be having we can look out for? So this is my exact flange, the internal part. This is my exact core pipe where my actual part of my actual fluid is going to flow into this segment, into the piping segment from one end to other end, from pump to vessel or anything. So this pipe segment is called as my core piping. And next comes my jacket piping. The outer pipes which is happening, that is my jacket pipe, which through which my hot fluid will be flowing. It could be your steam, it could be your hot water, hot oil, or anything. Some any tracing elements or any hot fluid, any jacket fluids, hot fluids compared to higher temperature compared to our actual fluid will be flowing on the external surface. Now, the major thing, the material of my core pipe and jacket pipe might be same, may not be same. It depends on the requirements and everything. It would be varying for me. Now there are lots of things which comes into picture. First, as far as core piping, it's a regular pipe which has the regular piping segment, so that goes there. But when it comes to your the other segment, the jacket piping, the first component in your jacket piping will be your end plate. So this end plate is nothing but your plate which is welded to my core piping, so that this plate will never move from my core. So it takes my core. So this part is my end point of my jacket piping. So this is the other things. Then comes your spacers, which will be present in your core piping. So spacer is nothing but a small pipe segment which maintains the distance between your core and your jacket pipe where your spacer can be. So what exactly it is, we'll see it in our next slides. Then we have them split pipe. So mostly to have some splitting in between or some special requirements for our requirements. So that also we can have it in your split pipes. Then again, there are some cases where you have some jump over piping segments where say there is some special part coming into picture. Say for example, a valve where the jacket fluid details are not required for that to be coming around the valve. So in that condition, we have some jump over piping segments, mostly used for your steam transfers or fluid transfers in this over. Jump over, which should be your, for some cases for your condensate, for your upper side will be your steam, excess steam to flow out, everything will be having some jump overs coming into picture. So that also will be present, and you'll be having your, so when a jacket pipe starts, at the start point of your jacket pipe you'll be having your end plate, and at the end point of your jacket plate where the jacket is going to end over there also you'll be having your end plate. And this end plate may coincide with your end of your piping segment, may not coincide with your end of your piping segment. It depends on your applications and depends on your requirements. So that's how it will be there. And you have something called the spacers and everything, and other stuffs will be coming into your next slides. Spacers or your guide plate or your spiders, we can say it. So this shall be provided for supporting core pipe from jacket pipe and to ensure uniform gap between your core pipe and your jacket pipes. As the diagram explains, so we'll be having a spacer around the pipe. Now, what should be the diameter of my spacer? It might be equal to your inner diameter of your core pipe or slightly lesser than your inner diameters to have some spacer. So as because the name indicates as a spacer. And design spaces shall be as per the design guidelines. So this is one thing which we, and as a spacer requirements, it's mandatory that we need to provide the spaces in our support requirements as a stuff based on our stress analysis charts or spacing chart. We need to provide the spacer details. Then some partition plates or end plates shall be placed where the flow of steam or heating medium is interrupted for full jacket system. So in this condition here, the flow of steam is going to be interrupted between this segment. So I need to have my end plate so that the flow of steam is interrupted. So my flow of steam is not going to go beyond this end plate at any conditions. So this location, I'll be having my end plate in present. Then I have something called end closure. So end closure is nothing but to terminate my jacket piping. So if my jacket piping is getting terminated at the end in between your piping segment, then I can have my end closure for my jacket piping. It can be your cap type or plate type. It depends on the application which you work out or the fluid which is glowing. Based on that, we can have either your cap type or your plate type of your end closures. And jump over. The length for your single jacket circuit is limited and supply of heating medium cannot be provided separately for heat circuit. So most importantly, whenever we have some special parts coming into picture and where the jacket is not to be provided, then I cannot have a segment heating medium to start at each and every end point, say, or each and every start point of my jacket piping. So once at the start point, if I provide my heating fluid inlet, the other end should be only for my outlet of that or the end terminal only. It cannot have the entire details. So in that condition, these jump overs will be coming and playing a major role for me. So where exactly at this end plate where the terminal is coming, we'll be having a jump over side so that the fluid will automatically transfer to the next start of my jacket piping using this jump over piping segment, which can be of different diameters based on our applications. Then jacket medium, heating medium can be either your gas or your liquid. So it depends on again your availability. So there are some cases where we might be having heavy excess steam, superheated steam which is going off waste, that can be used as your jacket medium, heating medium. So that is also there. And your reinforcing ring plates if anything required or supporting canceps, everything will be based on your system. The supporting for the entire piping segment will be provided on the most of the on the jacket pipe, not on your core pipes. Core pipes, only the spatial details will be provided on your core pipes, rest all will be on your jacket pipes. Next, the major thing, the jacket piping modeling by associating nodal degrees of freedom. How does Caesar to construct the jacket piping? Mostly it will be constructing based on your nodal degrees of freedom. So how I'm giving my degrees of freedom in my software? My degrees of freedom is given based on my nodal freedom. That is no how providing through my restraints, how I arrest my nodes. Based on that only my jacket piping association is happening in Caesar. And Caesar or any for Caesar does not have, or the software does not have a knowledge that there's a pipe inside a pipe. So this is something which we need to be very careful whenever we are modeling our jacket pipings. So if both the jacket and core are fluid filled, the fluid density of the jacket must be reduced to avoid excess weight. So how do I reduce it? So I need to calculate the core diameter fluid will be different. Definitely the density of the fluid which is flowing into the core will be different. And the density of the fluid which is used as a heating medium. If it is steam, no issue for me. But if it is other than steam, like hot water or hot oil or anything, then I need to calculate the equivalent weight. The fluid density should be the equivalent weight so that the excess weight which is happening will not be considered in my Caesar. So the equivalent weight for the core portion, the space between the core and your jacket pipe, that is only taken into my Caesar. So accordingly, I'll be giving the fluid density for my jacket system, or the entire segment, so entire system I can give it. Then if the system is exposed to wind, wave or anything, then these details are not going to be given in any of your core pipings. And it has to be given only on your jacketed piping only, the external pipe, because the wind wave is not going to affect anything in your core piping. The jacket is the one which is going to face it first. The effect of that is going to come onto your total system, but the one system which is going to face is your jacket piping. So it has to be performed on the jacket piping only. Insulation thickness set as 0. Suppose say there are some cases where there is some insulation given on the core piping insulation cannot be taken into consideration. The thickness should be 0. Manually also we can make it as 0 also, and we can proceed for the analysis. A simple modeling plan for your details for explanation, which we'll see it in the live software itself. So internal spacers here, this is my spacer. So I'll be modeling the spacer, connecting my jacket and everything, how it is going to be connected, those details. So here is my end cap. It could be your weld sewage used as welded sewage or end cap or anything. And then you have some rigid supports here. So this rigid support is present on my jacket but not on the core. But while modeling into my Caesar, there is some special requirements to be considered, so that also we'll have a look. And this is also I can look out for on your T sections. Wherever you are having your T sections, block fittings can be used for your jacket pipings and everything. So this is also one way of modeling your jacket pipings. So let's go for the further details. So what would be your first step in your modeling? The first step in modeling of any system is to consider the most efficient way to create input, and more importantly, the review of your results. So how do I review my results? So I need to know the review of results. Everything in Caesar or in matter of thing, any analysis software is mostly considered based on your node numbers, the routing methodology. Say if I start from A and I have to go to D, I need to follow A, B, C, D. I cannot go in zigzag manner. So if I go, I'll not be able to understand the review, because I'm modeling it. I can review the results very easily because I know how I modeled it. But say this same thing is going to person 2 to review the results, then he will be having a confusion. He may not understand our modeling methodology. So it's better the modeling methodology is followed in a easiest, simplest, straight model. So based on the most important scheme which need to be followed is your node numbering scheme. So how I need to have my node numbering scheme? So the standard methods for our node numbering scheme would be in this sequential order. That's by default in the most of our Caesar analysis we follow. But how do I link this with my jacket? That's the primary thing which plays a major role here. Then based on once you do that, the rotation, the duplication, and all your include and exclude options will play an advantage for the model which we generate, where if the node numbering scheme is set first. A small explanation taken from our example problem from user guide. So here I'm just differentiating my model with different schemes. So schemes I can make it as a segment like things or anything. So a pipe moving in one axis along a particular axis. So I'm making it as one segment. The second segment moving in the other axis, and the third segment. So if I'm very much convenient, I can make my system in a single flow in the same system, or I can make it in a different fashion. Each segment I can have a unified node numbers also possible. So it's up to the user who is going to model it. And based on his requirements, he can follow this unified system also. And it's not that this is the only system to be followed, because as a user, as a starting user, I might feel this convenient. For a different user, he might have a different convenience, so he can go for his convenience also in this methodology. So based on the segments, we can make it easily. The node number splitting can be done. Once the node number splitting has done, then with the segment details, I can even easily model my system. This is the segment details or to be specified on your core piping, not onto the jacket piping. Why? There are few cases where on the jacket pipings, there are few cases where especially where these elbows are coming, bends are coming, they might be there saying that the jacket is not required on those segments. So in that conditions, I need to be, I'll be modeling only the segments of jackets. So that is also a different things. So that's where that way also I can go for proceed further on it. So what are the steps or what are the input details which are need to be considered for during my core pipe modeling? The primary thing, the temperature, pressure in my core piping should be equal to the process line temperature details. It could be a design temperature or operating temperature, pressure, everything based on your requirements. Wind wave or earthquake need not be applied on your core piping model. It can be taken onto your jacket piping model straight away. Now, the bend diameters on most of the core piping until unless not specified will be equal to your large diameter, that is 1.5D by default, until unless specified. If say in my piping specification, the diameters, the bend diameters are specified as short diameter, short radius bends. Sorry, I'm not speaking bend radius. This bend radius, it's not bend diameter, bend radius. If it is given as short radius bend, that is equals to 1D, then I need to follow that. If it is not specified anything, the default diameter bend radius would be my large radius, large diameter bends. That is 1.5D by default. And wherever my spiders or spacers are coming with between the core and jacket pipe can be modeled as vertical or guide restraints on my core in connection with my jacket piping points. Suppose, say at node number 40, I have a core spacer coming into picture or spiders coming into picture. So on the core piping, I'll model with it as a restraints, which is nothing but my guide support guiding it all records. So since on the horizontal segment, I cannot provide all guides. So vertical support and your guide support. I'll model it, and the connecting node for that model spacer would be on my jacket pipe. So that is what I'll be providing it over here in that model. So that way I can model it over here. Then, and if in case there is some support which is provided on your jacket pipes, then it's advised that a node number be specified in your core pipe also, where a jacket pipe is getting supported. It's advised to provide a core node number at the core pipe also, so that it will be easy for our the displacements and other stuffs, everything. And the start and finishing node to rigid node should be defined as restraints, which will help to connect the core pipe and the jacket pipe. Say my start point is some rigid points. Say it could be your equipment nozzle point or some rigid non-rigid point. Then in that condition, and your core pipe and jacket pipe are starting from the same location, both need to be anchored and interconnected. Then only it will be intermoving easily. And next, the rigid elements shall be modeled as normal modeling procedure. That is nothing but your valves or strainers or some special elements or anything coming into your core piping segments. That can be modeled as your regular model itself, as we do in our regular model. This is the major thing with respect to your core piping model, which is nothing but your regular model, except to these spiders and the other details. But other than that, whatever we proceed, we use it in our regular piping modeling. The same modeling procedure can be followed in for modeling your core piping models. Then coming into your jacket piping model, the as far as Caesar is concerned, the easiest way for modeling your jacket pipe is to just duplicate your core pipe and the change your diameter and the thickness as per the jacket pipe specifications. That's the easiest and the most simplest way of modeling your core piping. Okay, and in most of the conditions, the bend radius for your jacket pipe would be your short bend radius only. Now comes the pressure temperature of your jacket pipe. What should be my pressure and temperature of my jacket pipe? By default, the pressure and temperature of your jacket pipe would be equivalent to your heating medium. Whatever is the heating medium going to flow, that would be your pressure and temperature by default. And most of the supports of the segment would be provided on jacket pipe portion only. And the most important thing is the fluid density of my heating medium to be used in my jacket pipe, because this is the one thing which is going to be flowing into my fluid jacket pipe, which would be coming giving me the total equivalent weight of my piping segment combined with jacket core and the fluid. So whenever I have these kind of segments, whenever there is an heating medium, if the heating medium is steam, then the fluid density can be set to 0. But if it is any other fluid, so the equivalent fluid density need to be calculated and provided by the user. So now what is that equivalent fluid density I'm speaking? Now whatever is the space left after the core pipe between your jacket pipe, for that only your fluid is going to flow. It's not going to the entire jacket pipe. If I give this one, the weight which has been estimated will be more than the actual weight which is happening. So which is nothing but yielding me the wrong results for my analysis. That's the one thing which you need to be taken care in the while modeling your jacket modeling. So now let me take you to the software straight away, and then we'll come and see for the further details. So I'm going to start from the basics of my modeling for the core pipe and everything. And the model would be similar to what we have seen in our regular model. This is just a simple model. I'm not going to go for any high-end models or anything. Okay, so let me start. Simple model. I'm assuming the diameter of the pipe to be 8-inch, which is standard schedule. And I have my fluid density. I'm assuming it to be some viscous fluid. So I'm just giving the viscosity value, that is specific gravity value. The temperature, I'm assuming it to be around 200 degrees centigrade, degree Fahrenheit, because this is in English units. And the pressure, I'm to 25 psi. Material, I'm assuming it to be 106 grade B. And the corresponding code is here 31.3. So this is what it will be changing. The first thing, the node number at node. Let me activate my node numbers. So this is the default node number, which is starting with 10 to 20. If you want to follow, you can follow the same node numbers, or you want to change some node numbering details, you are free to do that. The node number sequence is something which we are going to set. The user is going to set, and based on that only everything is going to come out. So based on the convenience of our modeling, the node numbers, the node number variations, the increments, everything can be set as per our requirements. Some prefer to have the increment at 20s, some prefer to have the increment at hundreds or 50s. So it's up to the user to decide the nodal increments and the start node numbers also. The first and foremost thing, node number 10 will be anchor. This is my core piping anchor. And then this node number 10 is going to be connected to my the jacket piping. So the jacket node number, I'm making it as 1000, and the anchor. Say for example, there is some spacer here or anything at node number 20. Then I do need to model this spacer with Y and your guide, or even the axial supports also can be given like Z. Anything is correct. Both are correct. This is the second part of my jacket. So say in case there's a bend here and the jacket is also flowing along the bend, then I need to have my spacers and everything. So let me activate my bend here, and I can have my bend node numbers as per my requirements, so that it would be easy for me for my model. And by default, the bend radius would be long radius. Or if in case you have some user defined radius like 4D, 5D, 12D, or something like 6D, anything based on the application, it might be changing, especially the slurry lines or everything. That diameter can be easily given, straight away given for us. It's not mandatory that it has to be 1.5D only. No, not necessary. Based on your piping specification, bend radius for your core piping can be given. And say 1030, your Y, and your Z. So I'm changing this to X, Y, I'll say you later. In between, let me put the other node numbers also. It will be Y. And this will be Z. Now in this bend, there are in our Caesar, we do have the modeling of our bend. Bend is a separate element. It does not come along with your pipe. So here I'm modeling my bend as a combined model with my pipe. So the bend before, there are chances that we place a spacer just at the start of your bend, and once the bend is completed, then I will place spacing my next spacer. So in this condition, the node number 25, where the node the under the bend properties are given, my bend angle is 0, so which is nothing but at the start of my bend. So I am assuming that to be the first spacer at 25, and node number 30 is nothing but my end point of my bend, end node number I can say. That I am basing my, which will be the next change of direction. So here I am space used at X and Z. So the next change of direction is my Y direction. So which I am assuming it to be 6 feet. And let me provide uh, with my X, or straight away I can go for guide. Both are same for my vertical member. To be more precise, it's better instead of guide, we can go for your axial modeling, axial stoppers, sorry, axial supports, sorry, the lateral supports. Z, and this will be 1040. Again, let me make it as 4 feet. Okay. Now I'm going to model my bend. So the spacers for my bend individually I need to give it. So which would be, yeah, this is your vertical. So this will be 1050, and I'll say X 50, 1050, say Z. So this is on the vertical member. 50 to 55, I'll make the node number, new node number as 55, as 1 feet. Sorry, then this will be, I'm making it to be in X. So again, it will be 1 feet. So the previous element, activate your bend. So this comes your bend 55 to 60. So on this, the next spacer I can provide it 1060, which would be your Z, and your Y. So again, 6 feet, I'm just modeling. Now, if in case I have some rigid element, so my terminal point ends here, or say I have some special support on my jacket in this node number. So I'm just giving it continue. I'm just creating a node number so that this node number is linked with my jacket support, which is going to happen in the later cases. Okay. Now I have some special rigid element coming into this picture. So let me take that rigid element to be some valve or anything like that. So let me go for the rigid, give the weight. So 450. And say symbolic error. This is a new feature in our 19, so that also I can use it. So whenever I get these kind of things, so here, or as per the valve, there is no jacket piping on the valve, so I need to terminal my jacket piping. So the way of terminating my jacket piping, I need to weld my jacket piping onto this area, so which should be coming in my jacket portion, not in the this portion. So let me go further. Again, 6 feet. Again, I'll go further. I fit, and I'll provide an anchor 2110. So this is the things which has been provided here. Spacers and everything, if you require, you can provide, or if there is a spacer between just closer to the terminal points also can be provided. So let me provide some spacer here, 1080, and this is your Y, 80, 1080, and this is your Z. Okay. Now this, say for example, this completes my major core piping. Now the next major important time is segment is for modeling my jacket piping. So the easiest way in Caesar is to duplicate the core piping and change the jacket piping. So how do I duplicate? Select it, right click on the element, go for duplication. So identical, I don't want to change anything, so I want to have it as identical. Just give your nodal increment as 1000 and say okay. But whenever I do this, one thing which is going to happen is the supports, everything is going to be getting duplicated. Okay, so this is my next core piping details. So core piping, I am assuming the fluid to be steam. So my fluid density becomes 0 here. The heating medium, so I'm making it as 350 degrees centigrade. Pressure, I'm assuming it to be 5 bar or 5 psi or anything, or say I'm making it as 15 psi. If you want to change your material of your jacket, you can change it, or if it is the same material, you can use the same material. That's up to the requirements based on the piping specification. Now in my core piping, the most important thing, this is going to be anchored, and I don't have the other things. So just I can delete the other supports, which is not required for me. Only the end anchor for my core piping is required, which has been modeled here. And to make my most specific, the core diameter. So I'm making it as 12-inch and standard schedule. Now let me do one more thing in Caesar, where I can do one more thing where I can assign my line numbers and change my colors in my piping segment. So I'll go for line number. I'm assuming the core piping to be in this magenta color, and the jacket piping, let it to be the same color, but I'll change the transparency to 40%. So here is my model. So internal, the magenta color is nothing but my core pipe, and the outer pipe is nothing but my jacket pipe. So node 10 is done, node 20. Okay, now comes, anyway, this is under the core, now into the core pipe, this is not required. So the next most important is the bend. So the bend, I have special requirements on my bend for my jacket. Here is, I have a support at the bend node number. So I'm providing a support here, which is on the jacket. Then the bend property, if you look over very closer, this is not happening properly. So the bend property, it has to change to short radius. So the bend is created properly for me. And similarly, the next element I need to delete because that's not required for me. Even here, this is not required for me. And here on the bend, if you say you have some node numbers or anything, then I can provide my support on that bend also here. But I'm not having any support requirements on the bend, so I'm not going. The one thing which I need to change is my bend property, which should be made as short radius. So once that is done, I can proceed further. So here I want to provide an hanger. So I can provide which is on the jacket pipe. And the next, so here it is terminating. The jacket is getting terminated here. So I need to anchor that point. So that is nothing but my end cap of my jacket, which I'm anchoring it here. And this anchor has to be moving along with my core. So whatever is the core node number, I can give it here, which will be 80. Similarly, on this area, I don't want this support, but I want to have a special support at 1090, and which is nothing but again into the core pipe, welded over the core pipe. And the last, only the core pipe. So this is the primary thing with respect to your jacket. And here there is no jacket. So how do I delete it? So this pipe, I can straight away delete it. And where is the delete? Here. The segment is not required because that is my jacket over the valve, which is not required for me. Let me rotate and show you so that it will be clear for us. So this is how it will be present. So this way, this is the simplest and the most easiest way of modeling your jacket. Okay, so I can straight away go for error checking. If there are any modeling errors, I'll be just definitely getting it here. And the most common thing on the bend curvature, you'll be having some node number differentiation coming as a warning. So that's not a problem. Say in case unknowingly I have given my jacket more fluid density, then my density of the fluid, suppose it's water, I given it as water. Sorry. Go to the first element of my jacket and I give the fluid density as water, say for example, and I check, I'll have a different weight because the weight will be very excessive, which is not required for me. So I'm making this density as 0, which is my steam. So the steam weight only will be coming with the core and the jacket pipe and the other spaces which is happened here. So if this is done, the modeling is done and error checking is done, and the other details which are going to come onto my jacket, like your wind wave or the other stuffs, can be straight away applied on the jacket instead of your core. So that's the primary thing which is required for me. So I'm not going to apply anything. So straight away, let's run the analysis. Okay. No, there are two things which we need to look out for. So first, the nodal forces and the stresses. So now stresses are failing here, especially on the expansion thing. But where it is failing? It's failing on the core pipe itself. So this is something which is required for me to study on the core pipe first. Either my which node numbers exactly it is failing, or the system is not flexible for my core pipe itself. So that's one thing which you need to study. But nothing is happening onto my jacket pipe in this condition. So this is one thing which is thing which I need to study here in the details. So I'm not going to do any analysis of these things. So now let's take to the further presentation. So this is the thing. So what are things which we require in our jacket combined analysis when we perform? So there are chances that the buckling conditions might happen in my system. But currently the buckling details are offered only for my 31.8 in Caesar. So if I'm going with 31.8 and analysis, then I can go for the buckling evaluation in Caesar straight away. But if I am not having it, especially when you are working with 31.3 or anything where the buckling details are not, then I have to do for my buckling details or everything into node manually. So manually when I do, the pressure points or the force points at each and every node where I want to study, I have to do that in manually calculations only. So let me take you back to the presentation. So this is what we have seen it. So what are the things as a stress engineer need to be ensuring it in a nutshell? The weight of the core system, that is the jacket system, core system, and the combined system has to be verified and has to be matching your actual requirements. The core piping segment system and your jacket piping segment and your combined system has to match perfectly, because this is weight is the one thing which is going to be used in your Caesar as your input load. So that is one thing which as a stress engineer I need to verify before going for finalizing my analysis. That's the first thing which I need to verify. The fluid density onto my jacket piping portion has to be taken into consideration. Very things. Why? The fluid density accounts for the volume lost due to the core also to be taken into consideration, which I cannot take it, which I cannot take the details into my Caesar. Caesar does not do this automatically. So as an engineer, I need to reduce the density of the jacket fluid accordingly so that the equivalent weight is calculated by the software or by Caesar to automated. Then the most important thing, the piping system does not develop large axial loads in the core and the jacket or the equivalent anchors. So when I speak about other results, so these are things which I need to verify. The axial load should not be very large. There are a few cases where I might be using some X supports, or some cases I might be going for some spacers like this kind of spacers, or the end points, anchor points. I need to do not it should not have large axial loads. Now, the results of these axial loads, large axial loads, might mostly happen when you are having when the user is over restraining the pipe in the axial direction. The most common, or in some cases when we have different metals, the core piping segment is of different piping material and the jacket piping is of different piping material, then comes this portion. So I need to be very careful in that condition also. Then the displacements at elbows in all the operating cases need to be verified that the core pipe does not tend to move through the jacket pipe also. So if say the the space gap between your core pipe and the jacket pipe is something around 3 mm, the displacement, the bend displacement on the core pipe should not be greater than 3 mm. So if it goes beyond 3 mm, it is going to tend to move the jacket pipe also, which need not be, and this perform the scissor 2 does not perform this interference. So this interference we need to be done manually by the verified manually by the user. And the most important thing, the displacements at spiders where jacket and the core are connected, the displacement should be same for both jacket and the core. So this is the other thing which need to be verified by the user. So wherever I have the spacers or the spiders which is connecting my core as well as the jacket, the displacements on the core pipe segment, core pipe node number and the jacket pipe node number should be same. If it is varying, then it's a problem for us in our real-time works. The wind and wave loads, if any specified, are disabled on the core pipe. So the wind and wave loads cannot be performed on your core pipe. So that should be very much taken care. And also the insulation thickness on the core pipe is always set to 0, so that no insulation details are also taken into consideration for my core piping and segments. So this is something after modeling I need to verify, and after analysis also I need to verify. Apart from my details, what are the stress checks which I'll be performing predominantly? Standard stress check will be your sustained expansion stress check by default if you are following your according to the code requirements. Again, not always my standard and sustained only will be checked. Again, this also varies based on your codes which you follow. I need to be, according to my code requirements, the stress check has to be cleared. And any buckling loads coming into picture, or for very large diameter pipes, there are chances of buckling loads coming into picture. Then the buckling loads has to be calculated based individually for your core, individually for your manual calculations. Then how do I do that? The critical pressure for your buckling, which has been calculated, should always be less than the pressure load or the force load which is happening at that node point from Caesar. If this is very much less, the critical pressure calculated manually for the buckling, that is your critical pressure. Beyond that, if the pressure or the force goes beyond that element, then my system is going to buckle out. So that pressure force load should be less than the nodal forces which is coming from my Caesar. If I do that, because Caesar is going to give me the nodal forces, the critical pressure, if there is lesser than the Caesar to force loads are less than the critical force loads, then my buckling is not going to happen in my piping segment. That's one thing which I can take care of it. Then the weld strength check between your jacket and core pipe. The strength where for every weld qualifications, they are based on your weld strength. There's a strength standard weld strength formulation calculations available in our welding codes. So based on that, the force which is happening in my weld points, in my node points, or if it is less than that, then my weld strength is also qualified. Again, the deflection of your jacket and deflection of your core to be maintained within the permissible limits as per the core. So if it is for core, it should not go beyond, the displacement should be very much minimal, and it should not go beyond a limit that it is trending to push my jacket also along with it. So that's one thing which I need to be very careful. Then any external pressures coming into picture has to be qualified based on my piping material group designs. And the most important thing is your axial stresses. In my current model, which I explained, there's a huge axial stress coming onto my model at the bend point, so which I need to rectify it. So the rectification of my axial loads, that is because the model is very stringent. I mean, the modeling supports or anything I have given is very much closure. Standard practice we may not have, because this was just for an explanatory purpose. I had taken an explanatory model where the model is very closer. So I had these failures. So these are the standard checks, standard practice. Now, the question comes, do I need to perform only these checks? Not exactly. Not always necessarily. These are some standard, but apart from this, if the client end requires some special calculations to be performed, then that also to me need to be included for jacket piping analysis. And jacket piping, the client will be giving us the most common requirements for their analysis most common analysis requirements to be performed. So based on that, we need to qualify, and we can take help of Caesar too for getting the inputs which is required for my other manual calculations to be performed for my jacket details like buckling load calculations and everything, or the weld strength calculations or the buckling load calculations can be performed. The inputs for that can be taken from my Caesar for my analysis. So that comes to the end of my session.